For as long as humans have looked up at the sky, the solar system has been our greatest teacher and also our greatest trickster. It looks simple from a distance: a bright sun, some planets orbiting neatly in line, a moon that follows us faithfully, and a sky scattered with stars. But beneath that apparent simplicity hides a universe that refuses to behave the way our intuition expects. This is the story of 7 of the biggest lies we quietly tell ourselves about our own cosmic neighborhood, and how reality is far more beautiful, strange, and awe-inspiring than the myths. Today's journey is structured like a documentary. Think of it as a slow dive outward, from the sun to Earth's seasons, to our moon, to the bright stars that fool us at dawn and dusk. Each stop will take a familiar idea and then gently peel it apart, revealing what is really going on behind the scenes. By the end, the solar system you thought you knew, the one from school posters and childhood drawings, will feel different. Not less magical, but more. Because when the illusions fall away, what remains is a universe driven by deep physics, immense timescales, and an elegance that no simple myth can capture. Let's begin where almost every picture book and classroom diagram of space begins. Lie 1. The sun is yellow. Picture the Sunday. Chances are, your mind instantly produces a bright yellow circle, maybe with little rays around it the same way you drew it as a child. Textbooks, cartoons, emojis, paintings, almost all of them agree. The sun is yellow. Except it isn't. If you could float in space, far beyond Earth's atmosphere, and look directly at our star, you would not see a golden disk hanging in a blue sky. You would see something closer to pure, blazing white. The yellow sun is not a property of the sun itself. It is a side effect of our sky. The sun is what physicists call a nearly perfect blackbody radiator at a surface temperature of about 5,500 degrees Celsius. That means it emits light across a broad range of visible wavelengths: reds, oranges, yellows, greens, blues, violets, all streaming out in a carefully balanced spectrum. When those colors mix, the result is white light. So why does that white light so often look yellow from Earth? Because on the way down to us, it has to struggle through an atmosphere full of tiny particles: nitrogen, oxygen, water vapor, dust. These molecules are just the right size to scatter the shorter wavelengths of light, especially blue and violet, much more efficiently than the longer red and yellow ones. This process is known as Rayleigh scattering. The scattered blue light goes off in every direction. Some of it reaches your eyes from all over the sky, turning the dome above you into that familiar daytime blue. Meanwhile, what's left of the direct sunlight streaming straight toward you has had much of its blue portion removed. That beam, stripped of some of its shorter wavelengths, appears slightly shifted toward yellow. At noon on a clear day, especially at higher altitudes, sunlight can look almost white, bordering on harsh. Closer to sunset and sunrise, when the sun is low on the horizon, its light must slice through a much thicker slab of atmosphere. Even more blue and green are scattered out, leaving behind light that is richer in oranges and reds. The sun itself, as it sinks, looks like it has been painted in fire. But this is an illusion of perspective and air. Astronauts in orbit, above most of the scattering atmosphere, consistently describe the sun as a piercing white star against the black of space. It only takes a thin shell of gas around a planet to tint it yellow, orange, or red. The childhood drawing is not entirely wrong. It simply captures how the sun feels to us from the ground. From space, our local star is colorless in the most dazzling possible way. Lie 2. The sun is a giant ball of fire. The next lie might be even more deeply rooted than the first. Ask most people what the sun is, and they will tell you without hesitation: a massive ball of fire burning in the middle of space. It sounds right. It looks right. Firelight and sunlight feel similar on our skin. But in a literal sense, there is no fire on the Sunday. Fire, as we know it on Earth, is a chemical reaction, combustion. Something burns wood, gas, coal by reacting with oxygen, releasing heat and light. But space is not filled with oxygen. Between planets, The gas is so thin that it's practically a vacuum. If the sun worked like a burning log, it would have gone dark long ago. Instead, the sun runs on a process so extreme that it changes matter itself, nuclear fusion. Deep inside the sun, far beneath the surface we see, lies its core, a region where the pressure is crushing and the temperature soars to around 15 million degrees Celsius. Hydrogen atoms there are not gentle drifting particles. They are stripped of their electrons, squeezed so tightly and moving so violently that their positively charged nuclei can sometimes slam together and merge. Under normal circumstances, two protons repel each other fiercely. They both carry positive electric charge and want to fly apart. But in the furnace-like conditions at the sun's center, some overcome that repulsion and fuse, forming heavier particles, eventually producing helium nuclei out of hydrogen. Here is the strange part. The helium produced weighs slightly less than the original hydrogen that went into it. That missing mass doesn't vanish. It is transformed into energy according to one of the most famous equations in physics, E equals mc, 2. Even a tiny amount of mass multiplied by the square of the speed of light becomes a staggering amount of energy. Every second, the sun converts roughly millions of tons of mass into radiation. That energy fights its way outward from the core, bouncing from particle to particle in an unimaginably dense plasma. A single photon created in the heart of the sun can take tens of thousands of years to finally emerge from the surface, like a traveler repeatedly changing direction in an endless crowd. Only when it reaches the outer layers and escapes into space does it race freely, crossing the 150 million kilometers to Earth in just over 8 minutes. The sunlight warming your skin today began as raw energy in the core long before human beings existed, long before civilizations, perhaps even before some of Earth's great ice ages. If the sun were burning ordinary fuel, like coal or oil, it could never have lasted for billions of years. Chemical combustion simply cannot release energy at that scale for that long. Nuclear fusion is what makes a star a star. The sun is not a campfire magnified. It is a controlled, gravitationally confined nuclear engine, quietly and steadily powering our entire planetary system. Lie 3. The Great Wall of China is visible from space. Now let's turn from the sun and look back at Earth, because some of the myths we attach to the solar system begin at home. There is a legend repeated so often that it feels like fact. The Great Wall of China, people say, is the only human-made object visible from space with the naked eye. It appears in school books, documentaries, trivia games, even casual conversations. It sounds poetic. A single monumental structure, stretching so far that it can be seen by astronauts orbiting above the planet. But that story is not true. Astronauts who have orbited Earth, from the earliest missions to those on the International Space Station, consistently report the same thing. The Great Wall is extremely difficult, if not impossible, to see with unaided eyes from low Earth orbit. The reason is not its length, but its width and color. The wall may snake across thousands of kilometers of terrain, but it is only a few meters wide. From a distance of hundreds of kilometers, that is like trying to pick out a hair from the far end of a room. Worse, the material it is built from tends to blend in fairly well with the natural landscape around it. High-resolution satellite images can pick out the Great Wall in remarkable detail, but they do so using powerful optics and sensitive sensors. That is not the same as a human eye pressed against a spacecraft window. Saying the wall is visible from space, simply because satellites can photograph it, is like saying microbes are visible with the naked eye, because they show up under a microscope. What can astronauts see? They can distinguish entire cities as bright clusters at night. They can make out coastlines, mountain ranges, the pattern of fields and roads. But individual buildings, roads, or structures, unless extraordinarily large and isolated, tend to blur into the landscape. The myth likely survived because it flatters us. It suggests that our species has altered the planet in a way so grand it is obvious from orbit. In reality, our greatest imprint on Earth, as seen from space, is more subtle and diffuse: the glow of urban lights at night, the patchwork of agriculture, the smoggy hazes over industrial regions. The Great Wall is one of humanity's great engineering feats, but not a banner stretched across the planet. Lie 4. Seasons happen because Earth is closer to the Sun in summer. Of all the misunderstandings about our place in the solar system, this one may be the most widespread. Ask someone why it is warmer in summer and colder in winter, and a very natural answer appears. Earth must be closer to the Sun in summer and further away in winter. It seems obvious. Move closer to a campfire and you feel more heat. Step back and you feel less. Yet for Earth seasons, that logic fails completely. In reality, Earth is slightly closer to the Sun in early January than in early July. The difference is not huge, only a few percent of the total distance, but it is in the wrong direction for the myth. When the northern hemisphere is in the depths of winter, our planet is actually a bit nearer to the Sun than during a northern summer. So if distance is not the main factor, what is? The true cause of the seasons is geometry, the tilt of Earth's axis and how sunlight strikes the surface. Earth's rotational axis is tilted by about 23.5 degrees relative to the plane of its orbit around the Sunday. Imagine a spinning top that is frozen in a slightly leaning position and then glides around a circle while always pointing the same way in space. As Earth orbits the Sun, this tilt means that at certain times of the year, the northern hemisphere is angled toward the Sun, and at other times, it is angled away. When a hemisphere tilts toward the Sun, two things happen. First, sunlight arrives more directly, hitting the ground at a higher angle. This concentrates energy into a smaller area, making it more intense, like shining a flashlight straight down on a table instead of grazing it along the surface. Second, the Sun stays above the horizon for more hours each day. Longer days mean more time for sunlight to deliver energy to the ground and the air. Both effects work together to create summer, stronger sunlight, for longer periods, heating the surface more efficiently. When that same hemisphere tilts away from the Sun, the opposite occurs. The Sun's rays strike at a shallow angle, spreading their energy over a larger patch of ground. They also have to travel through more atmosphere before reaching the surface, losing some strength along the way. At the same time, the days grow shorter and nights longer, giving heat more time to escape into space. The result is winter not because we are farther from our star in any meaningful way, but because our orientation has changed. This explains why, when it is summer in the northern hemisphere, it is winter in the southern hemisphere, and vice versa. If distance were the controlling factor, both hemispheres would share the same seasons. Instead, one leans into the light while the other leans away. Over tens of thousands of years, subtle shifts in Earth's orbit and axial tilt slowly modify the intensity of seasons, contributing to ice ages and warm periods. But on the scale of a human life, the reason you wear a coat in January and a t-shirt in July is not that our orbit has pulled dramatically in and out. It is that our planet is gently nodding back and forth as it circles the Sun, changing how sunlight spills across its surface. Lie 5. Venus is a star. On certain evenings or mornings, low on the horizon, a brilliant point of light appears so bright that it can almost seem artificial, like a spotlight against the fading sky. For much of history, people have called it the evening star or the morning star, depending on when it rises. Songs, poems, and myths have wrapped around this object, associating it with love, beauty, and guidance. But this star is not a star at all. It is Venus, Earth's near twin in size, shining not with its own fire but by reflecting sunlight. Venus orbits closer to the Sun than Earth does. Because of this inner orbit, it never strays far from the Sun in our sky. From our perspective, it appears either shortly after sunset or just before sunrise, always relatively close to the horizon, never high overhead in the middle of the night. The ancient Greeks once believed that the bright object seen at dawn and the one seen at dusk were two entirely different bodies. They gave them different names and personalities. It was only later that observers realized they were the same planet, seen in different parts of its orbit. Venus looks so striking because it is both relatively close to Earth and wrapped in clouds that reflect a large fraction of the sunlight that hits them. Its surface is hidden under a thick, global shroud of carbon dioxide, rich atmosphere, and reflective droplets of sulfuric acid. To telescopes, Venus appears as a small luminous disk that even goes through phases, like our moon, waxing and waning as its sunlit portion changes from our point of view. Seen from space, Venus is not a gentle star of romance. It is a world of extremes: surface temperatures hot enough to melt lead, crushing atmospheric pressure, and skies cloaked in toxic clouds. Yet at great distance, all of that chaos is compressed into a single bright point. Calling Venus a star is an understandable mistake. Human eyes only know points of light, not their true nature. But once the illusion is stripped away, the story becomes even more dramatic. That piercing light in the twilight sky is another planet, roughly Earth-sized, orbiting the same star we do, following its own hostile and fascinating path around the Sunday. Lie 6. Shooting stars are actual stars. On a clear summer night, far from city lights, the sky can turn into a stage for one of nature's quietest spectacles. A tiny streak of light flashes across the darkness, then vanishes. Sometimes it is faint, sometimes bright and fast, occasionally leaving a glowing trail behind. People call them shooting stars or falling stars, and many cultures have linked them to wishes, omens, or messages from the heavens. But these sudden flares of light are not stars at all. They are small bits of rock and dust, burning up high in Earth's atmosphere. Most of the time, the particles responsible are no larger than grains of sand or pebbles. They drift through space along paths laid down by comets, and, to a lesser extent, asteroids. When a comet approaches the Sun, the heat causes its icy nucleus to vaporize, releasing dust and tiny fragments of rock into space. Over time, these fragments spread out along the comet's orbit, forming a thin, invisible trail. Earth, meanwhile, moves along its own orbit at about 30 kilometers per second. When our planet crosses one of these dusty trails, countless tiny pieces of debris plunge into our atmosphere at tremendous speeds, sometimes tens of kilometers per second. At those velocities, the air in front of each particle compresses and heats up. The particle itself becomes incandescent, its surface vaporizing in a brief, bright flash. What we see from the ground is that brief flash, a meteor. Long before the fragment could ever reach the ground intact, it has usually been completely destroyed, scattered as ionized gas and dust. If actual stars, true suns, each with a mass often hundreds of thousands of times greater than Earth, were to fall from the sky, the result would not be a delicate streak of light. The entire solar system would be torn apart. Stars are unimaginably far away and essentially fixed in their positions on human timescales, drifting so slowly relative to one another that it takes centuries or millennia to notice their motion. Meteor showers, like the Perseids or Leonids, occur when Earth passes through particularly dense regions of a comet's debris trail. From dark locations, viewers can see dozens or even hundreds of meteors per hour. Each one is the last dramatic moment of a grain of matter that may have been wandering the solar system for ages before finally colliding with our planet's atmosphere. The poetry of the term shooting star remains irresistible, but knowing the reality does not make the sight less enchanting. If anything, it enriches it. Each falling streak is a tiny messenger from the outer reaches of our planetary system, reduced to light in the thin shell of air that protects our world. Lie 7. The far side of the moon is always dark. Few phrases in astronomy have captured the human imagination quite as strongly as the dark side of the moon. It suggests a hidden hemisphere, forever cloaked in shadow, perhaps cold and mysterious, and untouched by light. It has inspired music, writing, and an entire mythology of secrecy and isolation. But the so-called dark side of the moon is not permanently dark. It receives just as much sunlight as the side we see. The confusion comes from the way the moon spins. The moon is in synchronous rotation with Earth, which means it takes the same amount of time to spin once on its axis as it does to orbit Earth once about 27.3 days. Because of this perfect lock, the same lunar hemisphere always faces our planet. The other hemisphere, the one we never see from the ground, is indeed far from us, but not deprived of sunlight. As the moon travels around Earth, both its near side and far side take turns facing the Sunday. When there is a full moon, the side facing Earth is in direct sunlight, and the far side is in darkness. 2 weeks later, around new moon, the situation has flipped. The far side is fully sunlit, while the side we see is turned away from the sun and lost in night. Every point on the lunar surface experiences a day-night cycle, just over 29 Earth days long from one sunrise to the next. Daytime on the moon lasts about 2 Earth weeks, followed by 2 weeks of darkness. There is no hemisphere that is always night. The far side remained mysterious for so long simply because our vantage point was limited. From Earth, we cannot see it. Only spacecraft, starting in the mid-20th century, finally photographed it. Those first images revealed a very different landscape than the familiar near side. Far fewer large, dark volcanic plains, many more craters. The difference has to do with the moon's internal history, its crust thickness, and past volcanic activity, not with a lack of sunlight. Calling it the dark side suggests something fundamentally incorrect about how light falls in the Earth-Moon-Sun system. Calling it the far side is more accurate. It is simply the hemisphere that is turned permanently away from Earth, not from the Sunday. Still, there is something haunting about the idea. Even now, when orbiters and landers have mapped and studied it, most people will never see the far side of the moon with their own eyes. It is a reminder that even in our own immediate cosmic backyard, there are perspectives we do not naturally have, and places that remain forever hidden from a single point of view. The deeper pattern behind the lies. Taken one by one, these 7 misconceptions might seem like small corrections. The sun is white, not yellow. It fuses rather than burns. The Great Wall is not visible with the naked eye from orbit. Seasons come from tilt, not distance. Venus is a planet, not a star. Shooting stars are dust, not suns. The far side of the moon is lit, not eternally dark. But together, they reveal something more important about how the human mind interacts with the universe. Our brain loves simple stories. We are pattern-seeking creatures, trained by evolution to favor quick, intuitive explanations. If the sun feels warm like a fire, we call it a fire. If a bright point appears in the twilight, we call it a star. If summer is hot, we assume we must be closer to the heat source. The universe, however, is under no obligation to be intuitive. The rules that govern light, gravity, atomic nuclei, and planetary motion are often subtle, mathematical, and counterintuitive. Reality hides behind appearances. That is where science enters not as a set of dry facts, but as a method of asking better questions. Why does the sun look yellow? Why do seasons alternate between hemispheres? Why do some stars move differently from the others? Why does the moon always show us the same face? Each answer uncovers a layer of structure. Atmospheric scattering explains the sky's color and the sun's tint. Axial tilt explains the rhythm of the seasons. Orbital mechanics explain why Venus hugs the sun in our sky. Synchronous rotation explains the moon's familiar face. The real solar system, the one that emerges from these explanations, is far richer than the one painted by simple myths. The sun becomes a long-lived nuclear engine, quietly turning mass into light across billions of years. Earth becomes a tilted spinning world, whose climate breathes in and out with the geometry of its orbit. Venus becomes a blazing neighbor, wrapped in clouds, a warning and a wonder. The moon becomes a companion locked in a slow cosmic dance, its far side alternately blazing with sunlight and buried in shadow. And the small things, dust grains turning into shooting streaks of light, human structures vanishing at orbital distance, remind us of scale. Our works are impressive up close, but tiny against the backdrop of a planet. Our planet is vast from the ground, but small compared to the reach of its star. Our star is immense to us, yet just one among hundreds of billions in our galaxy. The lies we tell about the solar system are not malicious. They are shortcuts, approximations born from limited experience. Correcting them is not about feeling foolish. It is about upgrading our mental picture of the cosmos, swapping comforting sketches for something closer to the real cinematic universe outside. The more these illusions fall away, the more a different emotion takes their place: wonder. Not the wonder of mystery for its own sake, but the wonder of understanding. The realization that the same physical laws that govern a photon's escape from the sun also shape a sunset, a season, and the trail of a meteor across a summer sky. Next time you look up at the sun filtered through the atmosphere, at Venus gleaming near the horizon, at the moon hanging like a lantern in the night, remember how much of what you see is guided by geometry, physics, and perspective. The solar system is not what childhood posters claimed. It is stranger, more precise, and far more magnificent.